Hello! Now we're getting to the good part. Why? Because we're going to be putting together all this theory that we've learned into an example that I'm personally super excited about. We're going to be exploring space, planets beyond our solar system, and finding those planets that are most likely to be habitable. That means planets that humans could one day live on, or potentially planets that might already support alien life. And we're going to be doing all this in Node, using what we've learned so far. The story starts with the Kepler Space Telescope. This was a state-of-the-art telescope launched into space in 2009. For nearly 10 years, it looked out into space and gathered data about planets beyond our solar system. Kepler observed hundreds of thousands of stars, and in doing so, helped us discover over 4,000 planets. And the best part? NASA shared all the data that Kepler gathered, which means that we're going to take a look. We'll get started in the next video. See you there. Welcome back. Alright, how are we going to do all this exploration of space using the data that Kepler found? Well, we're going to be getting our data from the NASA Exoplanet Archive. Why exoplanet? Well, exoplanets are just planets that live outside our solar system. They orbit other stars other than our sun. And we're going to download the table of data gathered specifically by the Kepler Space Telescope, which we can find under this link for KOI table, where KOI is the list of Kepler objects of interest, the list of things that Kepler observed that might be stars containing planets that could potentially be habitable for humans. Let's check it out. We have our Kepler data, and we could explore it here, but instead, we're going to download this table of data in what's called a CSV format, and we're going to read it with Node. So let's save that to our machine. Once our file is downloaded, let's move on to the next step. In VS Code, I've opened a planets project folder, and I'm going to copy that file we just downloaded into the folder. And let's just rename this file to, say, Kepler_data.csv. Okay, so what is a CSV file? CSV stands for comma separated values. Let's see what this looks like. The file starts with this comment here saying that this file was produced by the NASA Exoplanet Archive. And we can see that because it's a comment, it starts with this hashtag symbol. This is followed by a list of all the columns in this data file, which are also comments, and they have pieces of data like the name of the planet, things like the orbital period of the planet in days, and even things like the radius of the planet. And then there's some interesting information here around the star which the planet orbits. So the effective temperature in Kelvin of that star. or even the amount of gravity on the surface of that star, or its radius. This is all data that we can explore. All right, now below all of these columns, the next line in our file is this header of our CSV file, which contains a list of all of the column names which we were just going over. And it's followed by a list of all the data. We can see that some of our data points are numbers and some are strings, like the name of our planet over here, called Kepler-227b. Creative naming, I know. The key here is, because this is a comma-separated value file, all of these data points are separated by commas, and each row contains the data for a specific planet. Now, if we scroll down through this file, you can see that this file has thousands and thousands of different potential planets that were discovered by Kepler. In fact, if we scroll all the way to the bottom, we can see that there's over 9,000 of these potential planets. All right, now that we know what we're working with, let's get started exploring this data with Node. I'll see you in the next one. Welcome back. If our goal is to explore this question of whether we are alone in the universe, whether there's a possibility of life beyond Earth, and doing so by exploring the data that Kepler gathered by looking out into space, and using that data to find good candidates for humans or even alien life, we'd have to start somewhere. First, by reading in the data that we've downloaded. We could read our CSV file using the built-in file system module that comes with Node. But the file system module has no understanding of what CSV files are. When we read in a text file, it's just string data. Node will have no understanding that each line in our file contains a collection of data on a planet, or that each data point is separated by a comma. This is where our third-party modules in our NPM registry save the day. Let's do a package search for CSV and see what comes up. As is usual with Node, the ecosystem is rich, and so we have a few good options that we could go with. By far the most stable and most highly downloaded package that parses CSV files is this CSV parse package. That's the second result here in my list. It's really well documented, which we can see if we browse to the homepage. This means that it'll be easier for us to pick up exactly how to use the functionality it provides for us in our planet's project. And it provides a variety of different APIs depending on what we're most comfortable with and what exactly we're trying to do. If you learn these APIs, you should be comfortable working with any of the other available CSV packages. There's tons of pluses for working with this one, so let's get going and install it in our project. Now, remember, to use a package from NPM, we'll need to initialize our project in our terminal by using the npm init command. And this time we'll just be happy with the defaults. So we'll say -y to give us all of the default options. And now remember that the main file that we're specifying in our package.json is index.js. This is just the default name that Node gives to the main JavaScript file of our package. If you remember back to our discussion of index.js, we're not actually using any of the special behavior that Node has around this file. We're still keeping things really simple. So we can go ahead and create a file that matches that name. And before we write any code, we're going to install our handy little csv-parse package. We'll run npm install csv-parse. Now there's a lot of CSV packages, so make sure that it's csv-parse and not parser or any variant like that. Alright, so we have our package-lock.json and our package is installed in our Node modules folder, which means we can now start using it in our index.js, which would look something like const parse and then assigning the module returned by the require function called on the csv-parse package. There we go. Let's dive right into what we can do with this package in the next video. See you then. Welcome back. What is streaming and how do we deal with large data files in Node? That's what we're going to answer in this video. Looking at the introduction for our CSV parser, we can see that this package is a parser converting CSV input into arrays and objects, but most importantly, that it implements the Node.js Stream API, and that this provides alternative APIs for convenience, such as the callback API and the sync API. So there's various different APIs that we can use. Now, why does it do this? Why add all of this extra choice and complexity when it could just use one simple API? Let's look at the summary by clicking this API link. We can see that each of the APIs has their own advantages and disadvantages, even though under the hood, they're all based on the same fundamentals. Okay, so we've heard this streaming word thrown around, but what does this actually look like? Let's take a look. First of all, we see that this is the recommended approach if we need the most power, and that it ensures scalability by treating our data as a stream from the source to the destination. Alright, that's a lot of buzzwords, and what does it actually mean for us? Well, the story starts with the way we get events through our CSV parser. Notice that when we require this module, we can then call the result as a function with these brackets or parentheses, and then we can call the .on function on the result of that. We've gone full circle all the way back to, that's right, the event emitter. In Node, all streams are implemented using the event emitter, where the events are emitted by Node and we just react to the events on that stream using the on function. Now, why might we want our CSV package to use an event emitter? Say, instead of just returning all the data in our file all at once in a callback function, which we can see is actually an option. Well, let's think back to our data. That CSV file of ours had a whole lot of planets. Remember, it was over 9,000. This is quite a lot, but it's still likely to fit in our computer's memory. After all, each planet doesn't have so much data that it would overwhelm our modern computers. But what if we'd discovered millions of planets? The universe is vast, so this could very well be the case in our not-so-distant future. In order to be more scalable, that is, in order to support much larger data sets and to be able to work with them in a performant, efficient way, it makes sense for us to read in the data line by line, probably starting from the start of the file and not from the end. But doing this allows us to handle data as it comes in, as it's read from our hard drive, rather than waiting for all the data to be read before we do anything with it. This allows Node's event loop in combination with our CPU and hard drive to all do their jobs as best as possible, so no one's waiting around needlessly. This is why we're going to be using the Stream API in combination with some of Node's built-in streaming capability. You see, many things in Node are streams, and we'll see this when we start working with HTTP servers and the web. We'll keep building up our knowledge and practicing this concept until we're really comfortable with it. For now, let's find some planets. On to the next video. Large data sets, and that we're going to be using the streaming capabilities of Node to read in the data from Kepler. So let's apply what we've learned. We've seen that the return value from our CSV parse module is a function that we can call like so. And that function returns an event emitter that deals with streams of data coming in from that file. But the parse function doesn't deal with files directly. It only knows about streams, which is where Node's built-in file system module is going to help us do what we need to do. So let's go ahead and import it. But what file system functionality are we going to be using? Just like the file system module allows us to open a file and to read it as a string of text, it also provides a function called fs.createReadStream. This allows us to open the file as a readable stream. Let's find out what this means. We can see that our function takes in the name or path to the file that we're opening, and that it gives us back a readable stream. This readable stream is a kind of event emitter that emits various different named events depending on what's currently happening to that file. For example, the file was closed, or a piece or a chunk of data was read from that file. There's also events when there's no more data to be consumed from that stream. That is, when we've reached the end of our file. And we also have one for if there was an error. Maybe our file doesn't exist. We can use these events to read our file in piece by piece. And every time a piece of data is received, we can do some processing on that data while we wait for the rest of the data to be read in. So for now, let's comment out this parse function and let's read our file by passing in the name of our Kepler data file to the function we just discovered, fs.createReadStream. This will give us an event emitter, which we can react to events from using the on function. And the most important function for us is going to be data coming in to our stream, which we'll receive in this data callback as a parameter to that callback function. With each chunk of data that comes in, let's create an array, which we'll call results, and we'll make it a constant, so we can't reassign the results, but we can update the contents by pushing values. So we'll push the data that comes in and store it in this results array. Now, when we reach the end of our data, let's just print the results that we've received. So we can actually call the on function again and do what's called chaining of different event handlers on our read stream over here. Because the on function returns the event emitter that it was called on, we can keep adding these .on handlers for different events that we might receive. So on the end event, we're not going to receive any data, but we will console.log our results array. And we can also just say that we are done processing our file. All right, now this should work, but let's be responsible and react to errors that might occur when we're reading our file. So for now, we'll respond to our error event, which gives us this error object in our callback function just by printing that error. This might occur if, for example, the Kepler data file was misspelled. So let's actually test this out and say we try to load Kepler data with 3 A's. What happens if we try to run node index.js? We get our error being printed out that no file or directory called Kepler data was found. So it looks like our error handler is working. We've actually shown that the rest of our stream code is on the right path. So what happens if we pass in the right file name? Let me clear the console, and we get this array of these buffers. These buffers are just objects that Node uses to represent a collection of bytes, because our read stream is just reading the raw data in our file as bits and bytes. So we're reading in our file and all of our potential planets, but we still need to parse the results and understand the values of Kepler's observations. That's where the fun really begins. So let's get to it in the next video. Welcome back. We now have the data from Kepler being read in as a stream, but the results we get back are just raw buffers of bytes. What we really want is for each piece of data that comes in our stream, we want it to be parsed as a row of a comma-separated value file. For example, as an object where the name of our column is the key and the corresponding value is assigned to that key for each of our columns. That's the functionality that our CSV parse package gives us with the parse function it exports. So what's the best way of approaching this? How do we connect the parse function with the read stream for our file? Well, because the parse function is designed to be used with streams, like our readable stream, what we can do is pipe the output of our file to the parse function like so, by calling the .pipe function on the stream, passing in the result of the parse function. What this is doing is it's connecting the two streams together. The pipe function is meant to connect a readable stream source to a writable stream destination, a stream that takes in data as opposed to giving you data. So the Kepler file is our source, and the parse function is the destination for our pipe. What does this look like? We have our Kepler planets data CSV file, and we read that file as a stream by calling the createReadStream function and passing in the path to our CSV file. This stream here can then be piped to connect it to another stream, this time a stream that is taking in data and processing it somehow. This writable stream here is the result that we get from calling the parse function from our CSV library. And the result that we're hoping for is a series of processed rows that we can read easily to explore the data in our CSV file, which might take the form of an array of JavaScript objects. That's what we're hoping to get back from our parse function. So we have our read stream that's being piped to the parse write stream. This is always how our pipe function looks like. It's always a readable stream providing the input for a writable stream. The data coming in and the data being processed, flowing from left to right. So let's see this in action. After our Kepler data is passed to the parse function, the data we get back from this stream, from this event emitter, is now going to be the parsed data. But there's a few different ways of parsing CSV data. For example, the comments that we use can start with various different characters. It's up to whoever wrote the file. So for the file to be parsed correctly, we can pass in an option to our parse function by giving it this object and saying that the comment character is the hashtag symbol. So now we're telling it that we want to treat lines that start with this character as comments. And we're going to pass in one more option, which is columns being set to true. This will return each row in our CSV file as a JavaScript object with key value pairs rather than as just an array of the values in our row. Now, finally, when we run our program, we get an array of all of the objects representing all of the data that Kepler discovered, being streamed in from our Kepler data CSV file. And we can see that all 9,000 of our rows were read. We went from a stream of bytes to nicely parsed JavaScript objects just by piping the CSV-specific parsing with the file stream that Node already made available to us in the built-in module. Everything fits together really nicely. Awesome. Now that we've read in the data, we're ready to do some searching. Let's find some planets. I'll see you in the next one. Here we go. Let's find some Earth-like planets that might support life beyond our solar system. At a high level, we're looking for planets that are similar to Earth, orbiting stars that are similar to our sun. And so we're going to want to filter through all of these objects of interest that Kepler found. First things first, there's many objects in our list that haven't been confirmed. We're going to want to filter out objects depending on this disposition property, where disposition just means the current status of that planet. So it could be confirmed, but it could also be just a candidate or even a false positive. And so we're going to take the name of this column and going back to our index.js, let's create a function which filters out only those planets that are habitable. So we're going to call it isHabitablePlanet, and it's going to take in an object or a potential planet, and it will return true or false depending on certain criteria. The first of which will be whether that planet has a property called KOI disposition, which has the value confirmed. And when we receive the data from our stream, from our Kepler data file, we're only going to add it to our results list if that piece of data is a habitable planet. So now our results list is actually the list of habitable planets. Remember that the parsed CSV data is now coming back as a JavaScript object, which has a series of properties matching each column in our CSV file. All right, now on to the fun bit. A review of the best available research we have on habitable planets was done in 2015, and it showed that one of the factors that makes a planet habitable is the stellar flux, which is a measure of the amount of light that the planet gets, or in other words, the amount of energy it gets from its sun compared to Earth. So as an upper limit, the planet shouldn't get more than about 1.11 times the amount of light that Earth gets. Any higher, and the temperature of the planet would be so high that any water on its surface would disappear. It would evaporate in a very short period of time. And at lower values, we have a limit of about 0.36 times the amount of light that we get. Any lower, and the planet gets too little light, and the temperature gets far too low. This stellar flux could be the most important factor for the habitability of a planet. Without the energy from the star, life can't survive. So where can we find this data in our CSV file? If we scroll to the section just above the temperature, we can see this insolation flux property, which is a strange sounding name That's just another way of saying stellar flux. So then we're going to take this column name and filter on the value for each planet. So we're going to say the planet must be confirmed and its stellar flux must be greater than 0.36, and that same value must be less than the upper limit of 1.11. So just a little bit more light than we get here on Earth, and about 3 times less than we get. We're getting there. Next up, studies of the Kepler data have shown that there's an upper limit to how large a planet can be before it becomes more like Neptune than Earth. These large planets are almost entirely made up of gases and ice, rather than having rocky surfaces that we could build on, like Earth. And the upper limit for the size or radius of the planet is 1.6 times the radius of the Earth. Back in our CSV file, we can find that the planetary radius is represented by this property here, measured in Earth radii, which is exactly what we need. So let's add on a condition which checks that the planet's radius is less than 1.6 times that of Earth. And there we have it. We'll have some really great confidence on how habitable our planets are just from these few checks. We could always do more by narrowing down other criteria, like, for example, the star's temperature and how that compares to the amount of light that the planet gets. For now, let's run this scientific marvel of ours and see how many new Earth-like planets we've found. So when we've finished reading our data, let's add a log using our template string that says that the length of our array is the amount of habitable planets that were found. All right, let's see what happens. Our program has found 8 matching planets that might support life, and our search has only just begun. The hope is that one day we'll be able to travel to these planets and explore them from up close. Imagine that. This is very, very cool. All right, in the next video, we're going to examine the data from these 8 habitable planets. I'll see you soon. Welcome back. We've worked hard and done our research. We've gone down from nearly 10,000 objects of interest that Kepler discovered to 8 potential new Earths. So let's take a moment to explore what we've found and confirm that our results actually make sense. When we finish processing our data, we could just print out the entire contents of our habitable planets. But if we run this, we can see that our data includes a lot of properties that we're not really looking at. So instead, let's look at the names of the planets that we've found and use that to confirm that our program is working by comparing it with the results that other scientists have come up with. We'll do this by mapping over our habitable planets array. This map function takes a callback that for each item in that array processes it somehow and returns a new value for that item. So we're going to use this to take our planets object that represents one item in our list here, and we're just going to return that object's Kepler underscore name, which corresponds to the name of our planet. So we're basically just filtering out or selecting the Kepler name property from each of our planets. And let's see what we get. Oops, I'm getting a reference error, so I must have mistyped the name of our parameter here. So it should just be planet, representing one item. That makes sense. And let's try it again. There we go. The names of our planets are Kepler-1652b, and so on and so on. But do these results actually make sense? The Habitable Exoplanets Catalog is a widely referenced source on habitable exoplanets. And they maintain this list here, which includes observations not just from Kepler, but from other telescopes as well. And you can see here at the bottom that they have 5 Kepler planets listed. Do their planets match ours? Well, let's see. Well, we have Kepler 442b and 62f, which I see are the last 2 listed in our catalog. So we're definitely on the right track. The results listed here are slightly different than ours because the exoplanets catalog is not updated as frequently as our data. And it also uses slightly different criteria than we did. However, our understanding of the observations made by Kepler and other Earth-based telescopes is improving day by day, and new observations are being made as well. If we scroll down on this page to the more optimistic sample of potentially habitable exoplanets, you'll see all of the planets that we've found and more. Our node application actually narrows things down more than this official list. We've come quite far just by looking at the available research and the Kepler data that's fully publicly available. I'll leave you with just one thing. If you look at our list of planets, one of the results that we see as one of the better candidates for an Earth-like planet was Kepler 442b, which we can see in our catalog as well. Given what we know, this planet might look something like this in comparison with Earth, which we have here on the right. This exoplanet is sometimes called super habitable because it might be more habitable than Earth. That is, it might have conditions that are better suited for life to thrive than those that we have here on Earth. That red color that you see in this depiction of the planet isn't necessarily rock, but actually plants and other vegetation on the surface of that planet. This idea is something that really caught me by surprise, so I thought I'd share it with you. All right. I promise we'll get back to Node now. But I hope you're as fascinated by all of this as I am. We can do real research on our universe in much the same way that we're doing right now. As an exercise, see if you can play around with our criteria here by looking at other research and maybe duplicate or improve upon the results that we've found. And on that note, I'll see you in the next video. Bye-bye.